So can you hear my screen?
Yes.
Yes.
Mhm. Okay. Okay, 45. Okay, let's start. Okay, so we in the previous lecture we finished on what we did. I will remind. Okay, we considered covariant and contravariant vectors and tensors. So we wrote the expressions how they can be transformed from one reference system to another reference system. And today we will consider some operations. So we will speak about general definition of the tensor, and also we will speak about metric tensor, and also we will look on some operation with the tensors, which will be important for us, and also we will look on some examples, for example, of metric tensor. Of course, I would like to say that when we speak about tensor analysis, of course, this is a big part of mathematics. So, in principle, I will give you what we will need for the following consideration of the general relativity. If some of you would like to investigate it much more deeply, the subject, so you can look on the corresponding books. But for us, it will be enough what I will give you. Okay. For now, I would like. Yes, I gave geometrical interpretation. For now, I will do some trick because for us it will be much more convenient to use it's not mathematically something different, but look, if before, for convenience for the beginning, we used two reference system like X and Xi. Okay, and when we wrote the representation of the vectors, transformation of the vectors, and tensors, we used this two system, X and Xi. Now I would like to make it much more convenient for us, and which is the same, doesn't matter. That now I will put the following notation. So now instead of Xi, I will call this the X prime. So again, the transformation which we would like to see, and transition of the vector from one reference system to another reference system. Now I again schematically to write like this. This is one reference system X with corresponding axis xi, for example, and we go to another reference system, and now I will call it X prime. So it means that if we have a coordinate, it's just for convenience, because later we will start to write bigger formula, and it's much more convenient to use this primes and additional letter. So it means that if we have, for example, vector with coordinates x here, xi, okay, in this coordinate reference system, we will have reference system or coordinate system. We will have x and you know, we need to write x prime I, because this is index, okay, which is x prime 1, x prime 2, etc. is here. xi, oops, sorry, x1, x2, etc. Okay. So, but we will do some tricks. So, for convenience, since it's not convenient to put a prime between letter and number, I just, if you agree, we will use x I prime. So it looks that prime in principle we need to put like this, you know, to prime to all coordinates. But let's convince that we can do like this, xi prime. So as soon as I write xi prime, it means that I consider reference system which are related with a prime reference system. Okay, so please don't be scared to ask me some questions. It's for free. You can ask any questions. If you don't understand something, please ask me. You can ask in any language which you would like. I mean, not of course in Chinese. Chinese, I don't know. Okay, so in this case, now I will remind, maybe on the next page, I will remind the transformation of the vector, so which is a tensor of first rank, and this is vector, okay? So, and we can even keep it in the mind, so it's not even important to look before, because we write, I want to write transformation or transition from one reference system prime to not prime, okay? So I will put A, okay, and since we agreed, I will put prime here, equal. Now I write the expression for contravariant vector. And since k prime, this is upper index, I need to put also here, as I know, I should remember that dx by dx a, and now I put indexes. So if k, since k prime in the upper place, I will put it here, also here. And after this, I need to put the summation index or dummy index, okay? For example, I. This is a contravariant component of the vector. For covariant, we remember that I need to put k prime here. Again, expression like this. Now I need to put indexes. So if k prime is lower index, I need to put it here also as a lower index, so in the denominator. k prime. And after this, I write the summation index, I and I. So which should be doubled. Okay, so everything in this case understandable. This is contravariant, this covariant. Okay, for the tensor of the second rank, and now I will write all three cases, and you can use it for the future if you would like to look at this. So similar way, so I write A. So the second rank, it means that I need to put two indexes, K prime, L prime, for example. Okay, after this, I remember construction. So construction such a way is that we need to put 2 times dx by dx, again dx by dx. After this, we distribute indexes, okay? Multiply and I. And now I look on the left side, so I can see that K prime, L prime, this is upper index, so I need to put it also here. And other indexes, their summation indexes, let's call it them as I and J. So, and I need to put, because we make a transition of contravariant component of the vector to the again contravariant component of the tensor, sorry, of the tensor. So, and I need to put here again as upper limit, upper indexes, I, J. And this is contravariant component. For covariant, I write here K prime, L prime. Again, I remember construction. Since K prime, L prime is a lower index, I put it here, K prime, L prime. And here I put summation indexes, I, J. And here, I, J, covariant. Sorry, how many people? And mixed component. So it means that one index contravariant, another index covariant. Again, I remember construction. So here I put K prime, here I put L prime. And after this, I distribute the summation index. So, for example, here I, here J. Since J upper index, I put it here lower, and here I. So this you can put in some frame. It will be useful for the future. This one and this one. Okay, so this is our important formula. In principle, we now can generalize what we wrote because it's understandable how we can write this transformation for the any tensor of any rank. For the 3 rank, we need to put multiply 3 times the x k prime by the xi and so on. So, and now I can give you the general definition of the tensor. So definition. The definition, so you can write, I will tell you, a tensor of type, or rank PQ is called an object, mathematical object, is called a mathematical object given by a set of numbers. Given by a set of numbers. Set of numbers, this is A. And now I will put indexes I1, I2. No. Sorry. Don't need to put parentheses here. 1, I2, I with index P. So you can see that we can put as much as we would like to put the number of indexes. Here, J. J1, J2, J2. This is index which has an index. Okay, I with index P, J with index Q. And so a tensor of type PQ is called an object given by a set of numbers. So this is a set of numbers in the coordinate system. This corresponds to coordinate system xi if a transition to the coordinate system xi prime, these numbers are transformed as the following. So if you are not in time, please tell me, I can repeat. So they transform such a way. A. Let's put here indexes K1 prime, K2 prime, K P prime, here L1 prime, L2 prime, LQ prime. So this is the same rank as we understand should be. And here we will put again, I remember this construction. And after this, I will put all indexes. So the first index is with K, K1 prime, K2 prime, KP prime. And here I invent the summation indexes. This is, for example, which we use now. We need to look here. I1, I2, IP. Okay. So, and after this, I again put takes, And here I will put J. Oops, sorry. J1, J2, J Q. And here I will put L1 prime, L2 prime, L prime. And I don't have place here. I will put it here. A I1, I2.
Sorry, in the last part must be LQ prime.
See, LQ. Looks like this one. LQ. And here we have IP. And here J1, J2, JQ. So this is a general definition of the tensor. So, okay. And the consequence of this principle of, as I already said, we will work with the tensors up to the fourth rank, which is a Riemann tensor. But again, don't be scared, because if you can see such a lot of indexes, you can say, Mamma mia, what we will do with this? You will see that due to symmetry, some symmetry of general relativity theory, cosmology, finally, our equation will be not so incredible complicated. From this expression, we can make some, as a consequence of this expression of this general definition, we can put such a kind of statement. So I like to say that the statement that if a tensor doesn't have any indexes, without indexes, we call it a tensor of zero rank. Tensor. Zero rank. So what is this? This is scalar. It's the same what is a scalar. And if we will look on this transformation, we understand that the tensor of zero rank, so the scalar, doesn't change from one coordinate system to another coordinate system. This is a point because it's important for us, because when we build some theory, we have some invariant which are not changed due to this transformation. In principle, you can remember much more simple definition of tensor. What is a tensor? So the first one point. So this is some mathematical object which is represented in the form of the table. So finally, this is some numbers which create some table. And the tensor, this is some mathematical object with a component of this table, like a matrix. The second, so this is a table. The second point, the tensor components are transformed by some rule. Okay, transformation by rule. So we know this rule. We have this rule. And the third one so this transformation of components which we used, this is such a way is that this transformation leaves some values unchanged. So we, due to operation with the tensors, we create some object, which scalar, which will not change from one reference system or coordinate system to another coordinate system. So we have invariant. This is, just to understand what is a tensor. And again, we remember that it's geometrically, this is due to the fact why we have this different kind of representation of the vector. This is due to the fact that we have an arbitrary reference system, arbitrary coordinate system. We can move from the flat space to curved space, and if we have a curved space, in this case, the coordinate net will be much more complicated. So coordinate axis can be not on the degree 90. So it can be even has some angle between two coordinate axes, or three coordinate axes. We also. Okay. Now I want also to show you some example, the behavior, some physical example. This is example how we can represent some physical objects, how called physical values, through the covariant or contravariant vectors. So the example, this is example, the first one. Let's consider the velocity vector. So, and for example, we have some vector, some motion from one point to another point, and we consider, let's call it like a dx. And this motion, okay, we will use some coordinate system. Schematically, I can write it like this. It's better. I will put Cartesian, it will be not so good. So in some coordinate system, let's call it xk. Okay, so this vector. And now I would like to see, and with corresponding velocity, okay, v, let's put it here, v, okay, velocity has a vector of velocity, has a component, corresponding component k. And in another reference system, it will be this one. So it will be dv components of the velocity will be dk prime, for example. Okay. So, and we want to understand how they will change due to the going from one reference system to another reference system, coordinate system. So we can correspond, this is dx k prime. So I can write that dx k prime. So if we will move this vector in another reference system, come back. In this case, we, from prime to not prime. What I need to write? So due to the mathematical analysis, we can write this is the x k prime divide on dx. For example, I can put here index even the same, but e I. Okay. In principle, even to be much more, I can, okay, oh, I like this. So if I divide the left and the right side on dt, I can have dx prime by dt equal dx prime dxi, and here dxi by dt. Okay, if now I will call the component of velocity, let's call it velocity dv prime with the components v k prime and dv without prime as a v I. Okay, I will obtain the following this formula. Let's put it in something like this. I will put it here. I will have vk prime equal dx k prime by dxi on vi, right? So what we can see? We can see that the component of velocity transform from one coordinate system to another coordinate system. The component of the velocity changed as a contravariant tensor. And which is a contravariant tensor of the first rank. Contravariant tensor first rank, which is, we know, this is vector. Sometimes much more convenient for us, especially when we will have long expression, we will, with a tensor analysis, we will use such a notation. So let's let's write like the xk prime on the xi. I can write it like this, xk prime and parenthesis I. Okay, so it means that we will use also important notation, which will make our formula much more elegant, that the derivation like this, we will use like this. Okay, just we put parentheses. It's Italian, sorry, comma. Okay, comma. Parentheses, this is in Italian. No, for me, sometimes I can mix Italian with English. So if you don't understand something, please ask me. Okay. So in this case, we can write the same expression, this one expression. We can write like vk prime equal x k prime, comma, I vi. Okay. So This is the first one. This is velocity vector. So we can see that transformation looks like a transformation transform like a as a contravariant tensor of the first rank. Now we can consider the other things. This is, let's consider some what is a gradient. So gradient, second one, gradient. So let's consider some scalar function f, which depend on coordinates, and in prime system it will be x k prime. Okay, and we want to see how it will transform in not prime reference system, coordinate system. You know, I all time make a, you know, like a reference system, coordinate system. So the difference is reference system and coordinate system. For now, we don't care, because reference system, when you use the coordinate system, when you are using the ruler, so to measure the distances in two-dimensional space, three-dimensional space. Reference system, when we use also, we would like to agree that reference system, this is also to use a watch, not only distance, not only scales, but also time. So for now, we don't care about this. We can, our indexes can be, doesn't matter, three-dimensional, four-dimensional, if you would like, you can put five-dimensional, so on. This is just a mathematical object. Of course, when we start to speak about physical values, of course, we can here, for example, say that k count from 1 to 3. Okay, 3 components if we are working in three-dimensional space. But in principle, what we are now doing with the tensors, this is a much more general case. So, and from k prime to, here we put k. Okay, and again, you need also to remember that if we are working with a summation index, for example, here, so doesn't matter, I can, instead of I, put any letter, for example, L, but it should be L, and here L, okay? Because this index, we can change the letter, but to be sure and that they will change it twice. Okay, so now we can write what will be with the gradient. So we have df, right, gradient. What is a gradient? So we need to consider df by, if for example, in Cartesian system, we need to put the component if df by dx, df by the y, df by the z, okay? In this case, we can write df by on dx k prime. And it will be df due to, again, mathematical analysis by dx k on dx k by dx k. Sorry, this I made it's not good, because it's better to put other index. In principle, we could put k, but dxi dx k prime. Okay. And if again I will call this one as a component of some vector, and since it's k below, I can put it here. This one I can call a. Since it's below, I can put I. And finally, I will have the expression like this: AK prime equal, I will put it here. So we can see that the gradient transformed from one coordinate system to another as a covariant tensor of the first rank. So this is an example. This is examples. Okay. Now sometimes I need to check that Zoom is working because so this is understandable.
Yes. Plus, minus.
Plus minus. Okay. So when we start to work with some examples, it will be much more understandable. Don't worry.
Sorry, is velocity is all cases contravariant vector?
Yes, you can see that I did everything honestly way. So you can see this, yeah. Behavior like.
So, and that's because distance is always coordinate vector. Sorry, covariant vector, contravariant vector. Because here we take then here is our distance vector is contravariant vector, and
No, but look, the point that I can show you here, the point that this when you transform this one, okay, so due to just derivation of complex function, you all time need to take this coordinate and to find derivation to this one. Okay, the xi will be in denominator. Just a second.
Okay, so next question: why we always choose that?
Just a second, I will answer. Just a
Okay.
second. Yes, sorry.
Okay, why we just cannot use, for example, for vector dx k prime below, and take derivative from dxi also below.
No, but look, you speak about this k prime. You can you can put it below here, for example, which is not convenient. But in any case, you need to, if you have some function f, which is or not f. Let's take it like f on coordinates x prime, y prime. So which and x prime is a function of z of x and y. Okay, so if when you consider the f, you need in any case to consider the x prime by the x, now by the x plus the x prime by the sorry, yes, by the y, like this. Okay, so the point that in any case you need to put this in denominator. Doesn't matter that you put here below. In any case, it will be, it will be here in this part of the ratio. We just for convenient we are using such a way that for convenience we are using to put here k prime as the upper index. But in principle, we can call it as you want. What is important that in any case all time you need to divide on another coordinate due to mathematical analysis. It's understandable? Or here, for example, it's better to put here.
No,
This tells us about lower
kind of
index.
understandable. However, if we use, for example, okay, if we consider as dx is a covariant vector, so we kind of need to have other expression where we have dx.
No, we will have the same expression. Let's call it how you want. So let's call it like just a dx prime. In any case, you need to take this, to divide this on something in below, which give us exactly as a result the low index. You know, this give us the low index. I mean that so this rules this work for in principle for the velocity vector, because otherwise you need to write, which is not convenient.
Maybe from mathematical point of view, that's right. However, if we consider definition of covariant vector, which we have before, for example, can we just change?
You mean that, yeah, you can, of course, if you will look, if you, for example, look on this,
can we consider
and,
k prime as a k prime as just xk prime, and will we have in this case xk prime which equal to derivative from xy by k by xk prime multiplied by also xi. Maybe that's not.
I don't
Okay,
understand exactly.
Okay, can we just change ak prime to xk prime, and also ai to
prime,
xi.
xk prime, and here if I will put, so it will be but you know, in this case we need to be very careful, because in another case we will have some. Oh, of course we can put xx, but I would like to take another value by the x and x. Okay, so here I need to put x prime I, which I don't like to put everywhere k, because everywhere x, because I would like to put here some another value, because it's a all coordinates. This is not a derivation, but in principle, if you are not for curiosity, yes, like this. If I would like, you know, if I
but here we consider that xk prime is kind of contravariant vector.
Yeah, we decided to call this, if it's transformed like this, we decided to call it contravariant vector. It's our agreement. So if it's agreement such a way that if I put here, I already understand which kind of transformation we are using. This is just the agreement. Okay, so
okay. So we
this is
just
agreement,
consider
yes.
something, and according to its transformation rules,
yes,
we decide
yes,
covariant or covariant. Okay,
yes,
so
yes. Of course, we could call it otherwise, but so we have an agreement with you that we will call this contravariant. but
Okay,
which
okay, so
yeah.
I understand. The object defines name, but name not define.
Yeah, exactly.
Okay.
Yeah, exactly. So if you decided to call this one, this one as a contravariant component, so as well as we received like this, we call it that this is contravariant transformation. So we can see it like this. So this is by our agreement. But here everything already mathematical. So we can see that this corresponds to this agreement which we did before. Okay.
Okay, thank you. Now it's more understandable.
Okay. So no, of course, ask questions because and don't be surprised that maybe something is not so understandable because it's not sometimes so simple. And this is only beginning. And I want to say you that you will have also home tasks. The tensor analysis too, which I will take into account for the final mark. Okay, on 13 people today. Okay, now I want to speak about metric tensor because it's not only important in principle, but also it's also important for to find the transformation of the coordinates. So write the title of this item, the metric tensor. So the metric tensor. Okay. So and in principle we can even to obtain due to some now some manipulation we can obtain the expression of the very important operation with the tensor. So let's consider some coordinate system with so when we use coordinate system, we also need to use some basis vectors, okay, which we can call let's call it E vector I. So this is basis vectors. Let's consider such that there is some rules between, and after this maybe I will consider examples. So I am much more tell about metric tensors. Example, let's consider the not example. Let's consider that between covariant and contravariant basis vectors, we have such a kind of relations delta ij, where delta ij, this is not 4 doesn't matter. I say it's not important. This is unit tensor. It means this is 1 when I equal j and 0 when I not equal j. So it means that we are using such a kind of orthogonal system. Looks like, for example, can try to represent this like this. And like this. Okay. So, and one reference system. So we discussed that we can use, we can work in any space, including curve space. And in this case, we will have, let's call it E1 for the case of two-dimensional, okay, E2. So the component of this basis is, we choose for now as a covariant. And if we have some vector, like this, R, in this case, we can find the component of this vector, putting perpendicular on this axis. This is perpendicular. And in this case, we can call it x1, x2. Just for convenience, we can do like this. Otherwise, we can put as a parallel and here we will put x1, here x1, here x2. So what is the idea? The idea is such a way that we can write the same, so it looks at, for example, we choose the coordinate system such a way that the E1 perpendicular to E2. Okay, so when, for example, we have a scalar multiplication E1 on E2, it will be 0. I just try even to write, to draw this like this. So, so you can see here like a perpendicular. So try to represent this geometrically. What is important? It's important that we can, if we consider in such a kind of representation in co and covariant vectors, we can represent the vector by two ways. In principle, we can write R as a x1, E1. I put here, you know, the indexes for the basis vector below. I can put because it's more convenient. So this is as a summation index plus x2. So x2, E2. But the same vector I can also represent as x1, E1 plus x2, E2. It's like a representation in two kind of components, in covariant and contravariant. And we remember that this mnemonical we discussed that in this case where it was here. Okay, so we can obtain the coordinate of this vector A by two ways: to put perpendicular and to draw the line parallel to the axis, to find a projection. So what we can see from this point, let's consider the element of the length of this vector. If we, as a matter, we can put here dr. Okay. So I want to find dl square, which I can consider as a dr multiply on dr. So from one point, I can consider it like this one, x1 e1 plus x2 e2. And again, we'll multiply on the same expression. Okay, sorry, I need to put here d and here d. What I will have this one, it will be e1 square, the x1 square, plus the square of the second summand, e2 square on dx2 square, plus 2 e1 e2 dx1 dx2. More general, I can rewrite this. So, for example, if I will look on this part, what is this? This is scalar multiplication e1 on e1. Okay, the x1, the same I can write for this one. So in general, I can write that it can be represented as some object, the x, and this object has indexes. Let's put it, for example, ik, and in this case also ik. And it is understandable that in this case, GIK, this representation of the combination of the scalar, scalar product, the product of scalar multipliers of EI, EK. This object we call metric tensor. Of course, we need to be sure that this object, which we now include, which call as it's transformed like a tensor. So it's if you receive something, I mean something which has two indexes, you can't immediately to say that this is a tensor. You need to check that this object is really transformed like a tensor. So for now, just believe me that.
I'm sorry, however, how our first term can be equal to expression which you write down of it.
Yes, so it means that this equal the L square.
No, I'm not about that. I'm about no. Here we have this e1 squared multiplied dx1 squared, and y
No,
it
this
is
is not
equal to.
No, this is look just okay. Go. You ask about this one.
Yes, I asked about this one and the expression below.
And the expression, this one.
Yes, okay.
Okay, so this, if you will write E1 multiply on E1, what is this? This is model E1 multiply on model E1 multiply on cosinus angle between E1, okay? Cosinus angle equal, this is, since this is collinear, it will be unity. So in principle, It will be just
Okay. That's equal to all expression, to sum of all three terms.
1, 2, 3. Mean this one.
No.
So look. I can write this one like this. Look, you agree with this? So dx1 e1 plus dx2 e2. And multiply the second the r. dx1 1 plus dx2 e2. Okay? So what I'm doing, I just multiply one summand on another summand. I can
Okay.
write here e1.
Okay, now it
Since
understandable.
this is
Can you
vectors,
just
I need to multiply scalar. Okay? This
can you
okay.
just put one more equality symbol because it looks like this vector. No, that's a scalar product of two vectors is that it corresponds to only first term of this long expression.
No, this is all of this.
Okay, now I
All of
understand.
this
However,
corresponds this one. Okay? No,
okay,
like
okay.
this. Sorry. Maybe it's not understandable. So, and this is the scalar product. So, I mean, okay. So, no, everything is equal this ik. So it means, for example, that J11, okay, what is this? This is E1, J22, this is E2, For example, J12, this is E1, E2. And if I now write, and you can compare this one with this one, in the representation of metric tensor, it will be J11 dx1 plus J21 dx2 plus J21 dx. Oh, sorry. I will write even 1, 2 dx1 dx2 and plus for two-dimensional space. So this is, I would like to say, if you will compare this with this, so it will be exactly correspond to this representation. Okay. So what is the point that this, let's put it in red, this metric tensor, and it's really transformed, we can prove it, that it's transformed like a tensor. For this case, you can see that J-E-K, this is a tensor of second rank, because it has two indexes rank, which call, and this is, in this representation, this is covariant, which call metric tensor. But of course, we can put as a contravariant expression for the metric tensor. So this one and this one will be right. If we want to write in another case, and now we will consider it. So we can the same. We can write like this. And this is representation. This is also a metric tensor J, IK, and this is contravariant. metric tensor. So everything working the same as for the tensor. Now we will see how we can obtain the representation and the operation with the tensor through the metric tensor. After this, we also will speak much more about metric tensor. What means this metric tensor? We will look on example. We will not look. We have a 5 minutes. But now I want to finish some things. The same. Look, I want to write also the same del square. I want to write to show what I wrote before, like this. I will not multiply twice on this expression, but I used this one and also this one. So what it means? Oh, sorry. I write x1 e1 plus x2 e2. Multiply, and after this I will use this representation in the covariant components. x1 e1 plus x2 e2. So what I will have in this case? I will have of course I need to put here d, here d, okay. So I will have e1 on e1, the x1 plus e1 e2, the x1 the x2 plus e2 e1 the x2 the x1 and plus e2 the x2 the x2. Okay, so now I remember that I used I use rule that I on ej equal delta ji. So again, okay, this is 1I equal j, 0I not equal j. Okay, so what I can see, if I will have not 0, so this will be 0, okay, 0. This also will be 0. So, and I will have that it will be E1, E1. And since this is a unit vector, so we the model of this vector equal unity, okay, because this is unit vector. So E1 on E1, the same index, it will be 1. So finally we will write that we have dx1 plus dx2 on the case of the example of two-dimensional space. So I can write that it will be dxi. Okay, if I now consider the previous result, this one, and I will rewrite it. So from one representation we obtained what we obtained just now. From another representation we found that dl squared equal I doesn't want to go to page. Save next. Okay, so I have G K dxi dxk. From another side, I have del square dxi dxi. So this is of course the same. This is just a different representation in this reference system, this coordinate system. Finally, if I will put this on left and this is on right, I receive from this, so let's write dxi dxi. I already rushed. Why I made a mistake because this is not right. The xi below here. I put the xi below. So okay, the xi, the xk. So this disappeared, and finally we obtain the important rule of rising of the indexes. So you can see that due to metric tensor, we can obtain the rule of rising of the index. Rising, this is rising, a rising. So it means that if you have contravariant component, something not right. Oh, it's so stupid. I'm sorry because I'm rush and I write now the stupid things and you didn't say me anything. The xi here, so we need this one with this one, and of course this I. So this is the rising of index. So look what we I want to finish now because we're already in time. It's already 3. So what we did, we applied on the contravariant component by the metric tensor, okay, and with the covariant component of the metric tensor, and as a result, we obtained here covariant vector. So it means that if you have contravariant, sorry, okay, if you have, yeah, right. If you have contravariant vector and you want to obtain covariant vector, you apply by metric tensor like this, okay? And we are common to use the phrase. In this case, the tensor take from the metric tensor, or vector take from the metric tensor, this index, free index ai. So this is the rule of a rising tensor. The same rule we can use for lowering of the index of the tensor. So, and we will consider in the next lecture. In advance, we also will consider the example of metric tensor and to play a little bit with a different coordinate system to feel what is exactly the metric tensor. What is important, and now you would like that you will put it as a mark in your conspect, that metric tensor doesn't tell us the space is curved or not. Metric tensor determines the property of the coordinate net, of the coordinate system. This is the point. So the metric tensor keeps the information which you know, which is peculiarity of the coordinate system, like this. But knowing component of the metric tensor, you will not say this is space is a curve, and with a curve, with which curvature, and like this. Because there is another tensor which really can tell you what is a space. We will consider it later. So, okay, in the next lecture, we will continue to work with operation with the tensors. Also, we will consider the examples, different examples, to understand much more deeply what is a metric tensor, because it's important, and all of our equations finally will meet the metric tensors, the component of the metric tensors, which is fundamental, because it's and like this, to prepare for the next step, which calls the covariant derivation. So, do you have some questions for now? The questions, I need to make a picture. No questions? Okay, question, are you here?
Yes, we are here. I think no questions.
Okay. So be sure that, not be sure, if you will present my lectures, believe me that you finally will work much more freely with the object in tensor analysis and with the equation and general relativity. So in the beginning, it looks like more complicated, but finally, all of you will understand how to solve Einstein equations and like this. So, okay, so we will meet Monday. Good weekend, and see you Monday.
Thank you.